Welcome to episode 311 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined today by my guest co-host, Matt Godbolt. Matt, welcome to the show.
Thanks for having me. It's fun to be here.
Yeah, it's been a while since we've had you on as a guest. How's everything been?
Been pretty good, thank you. Yeah, some things have changed in my life, but all for the better, and surviving the COVID thing just per normal. And, you know, I've found a new way to listen to podcasts rather than the commute now. I use it to listen to in the gardening. So I'm all caught up on CppCast and other things. And so pretty excited to be here as a co-host. Very
cool. Yeah, that's good. I should come up with more ways to listen to podcasts. I do it while, cleaning around the house and stuff like that. But there's probably more I could do when... more things I could do and listen to a podcast at the same time. On that note, I think we have mentioned before that you started your own podcast as well. Do you want to tell us a little bit about that? I did.
I mean, again, the COVID sort of standards, really. I started baking bread, making my own sourdough like everyone else did. I got a dog, which hopefully you can edit out any dog sounds in the background, but hopefully we won't have any. And I started a podcast. So I think that's all the standard things one does when one's locked in one's house. So yeah, to's compliment. We're on about episode 10-ish now with a colleague at work. But it's just a sort of general programming podcast rather than anything specific to C++.
Very cool. Well, I'll make sure to put a link to that in the show notes in case listeners want to go find that. Yeah, and at the top of every episode, I like to read a piece of feedback. This was a suggestion from the Include Discord, where we were getting some ideas of different topics and things to do for a podcast episode. And Antonio wrote to do a crossover episode with other podcast hosts might be interesting. Mostly thinking about the C++ related podcasts like CPP Chat, Two's Compliments, and ADSP or NDR. Can be another occasion to talk and think about C++, even if breaking the interview format. So we're going to do an interview today, but it is a bit of a crossover episode.
It is a bit of a crossover, right? I'd also add TLBH.IT as well as another sort of tech space podcast that I think, some folks you've had on the show I know are involved with. So yeah, well, here we are, the crossover.
There are plenty of CppCast guests who have gone on and started their own thing over the past year in addition to you.
But you were first. You were the inspiration for us all.
Well, it's been nice to be doing this for all these years. Yeah. Okay. Well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is Denis Bakhvalov. Denis is a compiler developer passionate about software performance. He currently works at Intel. Denis is an author of the book Performance Analysis and Tuning on Modern CPUs and a creator of the Performance Ninja online course. Denis is also a writer on the easyperf.net blog, host of performance tuning challenges, and regular Twitter Spaces talks about software performance. Denis, welcome to the show.
Welcome. Hi, guys. I'm glad to be here. And yes, seriously, just wanted to echo Matt that you guys are really legends, like Rob and Jason, being so consistent over the years. Like I actually started listening to the CppCast like since 2016 from the episode number 3, I guess. So that requires a ton of discipline. So that's really kudos to you guys. Yeah. And thanks for inviting me. It's a great pleasure for me to be here.
Yeah, well, thank you so much. And it's great to have you on. And I was just going to say that, Matt, you were telling me before, you've met Denis before. Is that right?
We've chatted over email, I think, over some of the things that Denis is going to talk about. So I'm super excited to sort of, well, first of all, meet him in person, but
virtually.
Funny quotes, and then hear what he's been up to and what he's done since we last spoke.
Awesome. Okay, well, Denis, we got a couple news articles to discuss. Feel free to comment on any of these, and we'll start talking more about what you're up to, okay?
Sure.
Okay, so this first one is a YouTube video, and this is making the classic Minesweeper game using C++ and SFML. And this one was really fun to watch. It's only about 7 minutes long, but the author kind of goes through the whole process of creating the game and the bugs he's run into during it. And yeah, it was very fun to watch, very entertaining.
It was a huge amount of fun. I laughed myself silly on that. But I have to feel like, as a sort of moral, if not actual representative, like of Jason, there was an awful lot of best practices that were being broken in the source code. If you actually looked in the background and paused the video or went and looked at the GitHub repo, I mean, it's a great format to get people interested in, to show them how relatively straightforward it is to make a game like that, like Minesweeper, and also with all the nice effects and everything. But I would say, I would question the quality of the code a little bit. It could be, sharpened up a bit, but it was a lot of fun, and I definitely encourage people to go and watch the video and have a laugh.
Yeah, definitely.
Yeah.
Okay, next thing we have is on the Visual C++ blog, and this is edit your C++ code while debugging with hot reload in Visual Studio 2022. So this is pretty cool looking. The C++ edit and continue feature has been a part of Visual Studio for, I think, a pretty long time, where when you're, on a breakpoint and the debugger has stopped, you can change some variables or insert some more code and then resume and actually change the program as it runs. But now you can actually just change your code without being on a breakpoint and then just hit this hot reload button and it instantly changes your application. It looks pretty amazing.
I mean, magic. I was going to say, as a compiler author, you must appreciate the sheer amount of magic that's going on behind the scenes to make that even feasible, right? I can't imagine what's going on.
Yeah.
Yeah, it looks very impressive.
Yeah, they must be doing a lot of stuff under the hood.
Yeah, definitely.
It's probably apart from Visual Studio, the editor itself, which is great, as a package, as an IDE, it's probably the one thing I miss from spending my time nowadays away from Windows is the ability to have edit and continue, which, as you say, it's been around for like 20 odd years now. I remember using it on like the original Xbox as a kind of, oh gosh, we got to the place where the game crashed. Hit the breakpoint. Oh, is it this? Oh, yeah, we can fix it and carry on and see if we get past it. All those kinds of things, which make a huge, huge deal when you've just been playing something for 15 minutes. Yeah, very exciting.
Yeah, definitely. Okay, and then the next thing we have is just a new version update for the speedlog library, and this is that they're adding support for formats compile time validation, which I think we talked about a few weeks ago when format was updated, and we went over a blog post about how this compile time validation works. So now speedlog can take advantage of that as well, which would be a really good change to get compile errors if you put in something wrong.
Absolutely, especially as those log lines that are least likely to be hit are probably the ones that are erroring in like panicked situations that you're not expecting. And if they happen to have format string problems with them, that's the last time that you want to find out, is when they're actually executing. It's like, oh, we crashed. Why did you crash? Oh, because there was a bad situation. And while logging it, we threw an exception.
Right. Okay. And then Matt, I'm going to ask you to go over this last article because you suggested this paper and it's very large. I read through the abstract, but I could not read through the whole paper.
It's very much like it's my favorite thing to happen this year. And it's certainly, given the confluence of being invited to co-host this and knowing that Denis was going to be here, it seemed too rude not to bring it up as something that came out. It's a paper that describes like the new state of the art of simulating the throughput of Intel x86 processors, including all of the really unusual internals that have to be modeled in order to get decent performance figures out. And there've been an awful lot of papers and work on essentially reverse engineering what's going on inside the chip that have been happening over the last few years. Agnafog and some of the other folks who are listed in this paper have done some things before, but this is like within like a cycle or two of real world measured performance for all the different various flavors of chips. So we're close to like a grand unified theory of what's really going on inside the silicon that Denis won't be able to tell us about for various reasons, I'm sure. But it's super exciting to me as somebody who works in performance in my day job. And it's just super cool to know and to understand how complicated these CPUs are inside and how many clever tricks they're pulling on our behalf to make our code go fast. So I was just reading the abstract and having an idea of it is cool, I think.
Yeah, this is actually a great paper. Yeah, so I just went through it like really quickly. Like I spent maybe like 15 minutes or so. But yeah, so it seems to be much more precise than than everything that we had before, like tools like Ayaka and like LLVM MCA. And then the problem is that, first of all, it's really hard to statically predict performance, right? Well, I mean, I don't know, but I mean, it's maybe even impossible to predict it super correctly. I mean, well, okay, to some extent, that's really hard to do. So, those tools that existed before, this new tool that they created in their paper, so they largely discarded the effects of various non-deterministic CPU units, like for example, any front end effects essentially were discarded by those tools. So what do I mean by that is that, for example, the alignment of the code was not in the model. Also, the tool, those tools always assume that everything is in the cache, so you don't ever hit the cache misses, and all the branches are predicted like pretty much 100%. Well, I mean, that's all obviously not always the case, right? So, but okay, so going back to the paper, right? So I think their work is based on the work that they did previously on this uops.info, right? So they somehow leverage these giant tables, which actually seem to be pretty much again accurate in terms of latency and throughput of individual assembly instructions.
They've got it down to kind of a fine art of how to like measure one instruction and sort of see all the effects that it has and deal with the dependency chains and all these clever things that they talk about. There's sort of a micro benching, a nano bench library that they talk about. But yeah, it's very exciting. And for me, it's, as you say, it replaces things like IACA, which hasn't really been supported for 4 or 5 years. And as you say, LLVM MCA is brilliant. But it's driven by LLVM's interpretation of what the CPU does, which is not necessarily very accurate. And having something more accurate can only make that better. And given that LLVM MCA is used by Clang to do the scheduling of the emitted code, it kind of will actually work its way backwards into a compiler eventually, and hopefully we'll get faster code, which is, nice. Everyone loves faster code for free.
Yeah, definitely.
Right. Yeah.
All right. Well, Denis, I mentioned while reading your bio that you have a book, a blog, and an online video course where you focus on performance. And I just wanted to start off by asking how you got to have this focus on performance in C++.
Well, let's see. Well, I mean, I don't know. I was always, interested in performance and making things faster. I think the first like, oh yeah. So I remember, those funny days when I just, like first tried Intel vTune. I think at that time it only, it required that you instrument your code. It was like back in maybe 2009. So you first, had to wait maybe half an hour, an hour. Well, I mean, depending on your application, but while when the vTune will instrument your code first, and then it will actually run and show you the profile. So those were the funny days, and I must say that at the time I had no idea what it is doing, how it's working, and so on and so forth. But I mean, when it showed you the list of hot functions and hot places, well, I mean, it was super cool and interesting. So I don't know. I mean, and then fast forward. I don't know how many years, maybe 6 or 7 years. I joined Intel. Well, I mean, so this was you can say it was a natural step for me. I don't know. So that's how I really started working on performance on a daily basis. Well, I mean, more or less. Yeah. So that's roughly the story. And then. And then if you like wondering about the book and how I get to that, this also actually came to me, let's say, organically.
Okay.
Well, I mean, so I started my blog roughly at the time when I joined Intel. This was around 2016, 2017 maybe. And so I began documenting things that I learned about performance, about the work that I'm doing at Intel, like this profiling thing and optimizing code and stuff like that. And then well, I mean, I collect some knowledge, let's say, on my blog, and then a couple of folks reached out to me like, hey, you have this, good information on your blog, but it's, scattered in a way. It's not, systemized. Like maybe you should write a book. Well, and so this is actually how my book, let's say, was born, I would say.
Okay.
So yeah, and then the online course, I think the same thing. My book simply lacked the practice piece of it. So well, I mean, I and then I decided to go beyond that, and maybe I can create some place where folks can practice optimizing and tuning their code. So this is how this Performance Ninja got to life.
Could you tell us a little bit more about that? I mean, do you find that people need to practice it, or is that what made you move to make a site to be able to practice these things, or is it, I mean, I know from my own experience that until you run that profiler, your intuition is 100% wrong every time. Even when you've accounted for the fact that that your intuition is wrong, you're like, I know where it's going to be, and you run the profiler. It's like, no, it's in Strucopy. What? I didn't even call those kinds of things. So, is that the kind of thing that led you to go no, people actually have to put this into practice themselves? And maybe tell us what Performance Ninja is.
Yeah, sort of. Yeah. Yeah. I mean, so I actually think that the performance optimization and tuning, is well, and I think it may become even more important than it was during the past 4 decades maybe.
Mm-hmm.
And I think there are a couple of reasons to that. So let's see. So first of all, I think that and it is driven sort of by the current technology. I mean, if you would ask me whether the Moore's law is dead, I mean, well, I mean, it's not the easy answer, but I think if you look from the software perspective on this question, from the software vendor's perspective, then I think the answer is yes. And what do I mean by that is that now software vendors should spend more resources on optimizing their code, because hardware does not provide major performance boosts anymore, unfortunately.
Right.
I mean,
those transistors are going into things that aren't making things faster. They're just giving us more capabilities, or they're making caches bigger, or things like that aren't necessarily directly related to performance in the same way as they used to, say, 20 years ago, when you could guarantee I'm going to get 1 more gigahertz in 4 years' time.
Right. Yeah. So I think especially I'm not talking about the performance improvements are completely gone. But if you look at the single-threaded performance, and this is still very much important. I mean, not only multi-threaded performance, but the single-threaded performance is also very much important for many client applications that run on your laptop. So that's the first thing. And then the second thing is that I mean, previously in the so-called PC era, where the companies that sell software, right? So this software will usually run on the client's machines. So software vendors did not pay for the electricity bills for their customers, right?
Right.
But now the situation is changing. So now everything moves to the cloud. Mm-hmm. And then so software vendors now pay their so-called cloud bills themselves.
Right. So suddenly it's their problem now. And so suddenly they're motivated to fix it. Whereas before they were sort of distributing it by, well, I have 1 million customers, I've got 1 million CPUs. Now they're like, no, I'm paying for the CPUs, right?
Right. And I think that those are two fundamental, reasons why we'll see, more people start, focusing more on performance. And I think that, those people that program in Python and other languages, they may be affected even more than us. But I mean, well, we'll see. Yeah.
Yeah. You talked about tuning a bit, and I just wanted to go into the tooling maybe a little bit more that you focus on when you're talking about performance tuning and teaching performance tuning in the Code Ninja class. Can you tell us more about your experience with tooling and what you like to use, what you get out of it?
What I like to use, let's see. Well, I mean, Intel Vitune is my sort of go-to tool.
Okay.
But I actually I think that more frequently I prefer just running Linux Perf, because it is installed on every Linux distribution that I'm eventually touching. I mean, for me, it's just simpler and faster to run Linux Perf than to unleash the whole power of Intel Vitune, let's say, if you will. So yeah. I mean, but for the most part, actually, Linux Perf is also a great tool. It supports most of the things that Intel Vitune can, but just there is lack of graphics interface, right? And that's sometimes that's actually hard to replace even. Like for example, yeah. Sorry. So for example, in Vitune, right, you have this this timeline where you can zoom in and filter in, and into particular in a particular interval of the when the program was executing. So that's a really cool feature that's that you cannot unfortunately do with Linux Perf. So I mean, yeah. But for the most part, Linux Perf is a great tool as well.
I was going to ask actually, what kind of things do you do? So maybe just for those who aren't as familiar with what Perf is, could you explain the kind of things that both Vitune and Perf are doing behind the scenes, and what kind of information you can glean from them?
Sure. Yeah. So Linux Perf is actually is a basic performance profiler, let's say. So what it does is actually just really simple, and the best way to explain it is everyone is familiar with the debugger, right? So debugger is essentially the simplest performance profiler, if you will. so you can view it like that. So if you will run your program under debugger, and you will interrupt it once per, let's say, per 10 seconds, and you will record the place where you stopped. And if you will repeat this process like over, let's say, 1,000 times or 10,000 times, then you will collect, then you will collect, 10,000 samples. And if you build a histogram on that, then you will be able to see where the program was interrupted the most number of times. So this will be your hottest place. And this is an oversimplified explanation of what profilers do under the hood. So they essentially are capable of interrupting your program a high number of times during a small period of time, and that's how they tell you where the hottest places in your program are. So that's I think the simplest explanation.
Right. And I know from personal experience that it's not just necessarily time that you can interrupt and say, like, every 100 seconds. You can say every 10,000th cache miss, tell me what the heck was causing the cache miss. And again, you can sample and group those. And so that's the kind of useful information you can glean that it's very hard to do in like in any other way, right? I can't tell you where am I missing the cache the most? And you're like, oh yeah, I'm walking a linked list here. Well, of course, right. Okay, maybe I shouldn't do that. That kind of thing, right?
Yep, exactly. Yeah.
So then Vitune on top of that is a more graphical way of getting the access to the similar kind of information.
That's correct. Yes. So yeah. So Matt, as you described, right. So this is actually a little bit more advanced usage of of the profiler. If you really want to know where exactly which line of code, which assembly instruction misses in cache a lot, or for example, which branch mispredicts, right? So that's where you sample not on cycles, but on some other event like cache miss, for example. I mean, yeah. So this is a more advanced usage, and actually, I wouldn't say I suggest this workflow, if you will. So and previously, well, okay. So let me first start why, right? And I think that it requires you to have a knowledge about all the different performance counters that are available, but there are hundreds of them, and and they're changing all like in every CPU generation. So you cannot, let's say, be well. I mean, of course, you can study, documentation and learn, what they are doing, what they are measuring, but I wouldn't recommend that. There is a better, I think, approach here, and there is a methodology called top-down analysis. So this actually allow you to characterize your workload from the CPU perspective, right? So it's like what like where the bottleneck in your application is, from the CPU microarchitecture perspective. For example, there are like 4 major categories. It's retiring, front-end bound, back-end bound, and bad speculation. Okay, we'll not dig into that, but the main point here is that it abstracts away the knowledge about performance counters, and it collects all the needed counters like automatically. You don't have to care about any specific meaning of them. You just run the tool. It will show you where exactly your bottleneck is. Like, for example, you miss in let's say L2 cache, or you go all the way down to the main memory. And after you figure out what is the type of bottleneck in your application, only then you dig, you locate the exact line of code where this problem happens. So this is a really powerful technique. I use myself with I use this technique myself. Pretty much. It's the first thing that I do actually, right?
So it's like gives you an overview before you go down the rabbit hole of like which of the 150,000 different counters should I be measuring. It's like, no, well, the first thing you need to know is that it's the problems with cache misses or the problems with bad speculation, and then you can dig and dig and dig down, and it gives you a very high level, relatively speaking, right? A high level view of where your performance or the kind of performance problems you've got.
Right. Yeah.
Okay. You were talking earlier about, what you think is going to be driving performance in the near future. Where do you see us going with focusing on performance? What can C++ developers do to, better handle, the way programming is going to change as we get new hardware, new software, new compilers?
Oh, that's a complicated one. So what can drive further improvements, right? And I think that, well, I mean, I would like actually to approach it from this perspective. So sure. There are so there are opportunities and there are challenges. So I don't know, maybe let's start with opportunities first. For example, what can drive, right? So I mean, what we as a software developers can do. So I think I think we can. So first of all, better compilers exist. I mean, in the future, and so I actually gave a talk on LVM performance workshop on February this year, and I tried to answer the question, what will drive the future improvements in the compiler? And so I was I was caught by this question. And so what I actually did, I asked a whole bunch of compiler experts what their view on this question is, and I just summarized the whole, this whole wisdom. And so so there is this, Probsting law, which says that advances in compiler technology make your software run faster. Double the speed of your of your code every 18 years. Okay, so it means that the performance improvements of the code that's generated by the compiler double every 18 years. Okay. Well, I mean, of course, it doesn't hold for some reason, right? So what it means that if you take the Clang compiler now, and for example, the Clang compiler 9 years ago, and you can expect the 50% faster code, right? Just from the compiler, only from the compiler. Okay. If you run it on the same hardware, on the same on the same operating system, and so on and so forth, on the same platform, but just a newer compiler. So some people actually think that it's now not the 18 years, but the 50 years, something closer to 50 years. So I mean, that's a really pessimistic view, I would say. And then going back to how we can make compilers faster. Well, I mean, there are actually multiple directions. But so what I was able to, I mean, the major directions are first machine learning, right? I mean, compilers are full of heuristics and cost models, so we can replace those with machine learning models. So that's first. Then the second is that there is a lot of work going on with synthesizers and super optimizers. So compilers sometimes miss some peephole optimizations and not being able to generate the optimal assembly sequence. Like for example, if we're talking about the SIMD instructions, it's sometimes hard to find the best pattern of assembly instructions with all those crazy shuffles and so on and so forth. So and that's the work that John Reger and Jeff Langdale and some other people are doing. So what I actually wanted to say is that that the conclusion around and actually, so one of the questions that I also was asking all those experts is that, like, what is our current headroom in existing LLVM optimization passes? And I mean, I think you will be surprised, but most of the people think that we are chasing the tail now, and
oh really?
Yeah, and the headroom for us is probably around 1%.
And so just to understand that, you're saying, like, with the existing infrastructure, with the existing set of or things that we know, there's only a few percentage points left without something else changing to make it go faster. Am I understanding you right?
I think that's yeah. So what do I mean by that is that if you will now go and try to polish all the existing LLVM optimization passes, like you are not expected to to gain more than, I would say, 1% on average, right? On average.
Wow.
So I mean, that's again unfortunate and pessimistic view, but yeah.
So what do you think needs to change? Where are we going to find the next explosion of performance? Does the language need to change? Do the compiler infrastructure? Is there something we're missing somewhere in the line of between programmer writing code and optimal code being produced? Is there something that we haven't thought about? Where's it going to come from?
Right. Well, I mean, and then so I actually and some of the folks also think that we should better spend our resources and I mean compiler technology resources on make better tools. So, well, I mean, because compilers already are great at parsing the code and and doing all sorts of analysis on on the abstract syntax tree and so on and so forth. So we can build a better tools that will help developers to to improve the performance of their code more effectively, right, and efficiently.
So when you say tools, you mean tools like Veentune and Linux Perf and things like that?
Right. Yeah. So and then actually, and then one of the tools that I'm personally dreaming about is something like that. So imagine you are writing, let's say, for example, imagine you are writing a matrix multiplication, right? So I mean, it's not super. I mean, that's a tricky one, but at the same time, it's not super easy to write super effective code, super optimal code for every hardware platforms. But okay, so what I would like to see is that, for example, there is some recommendation system that will detect that I'm writing the matrix multiplication code and will say, hey, I think you are writing matrix multiply. And I have
You're saying that Clippy will pop up and tell me it looks like you're writing a matrix multiply. Have you considered using the Intel library to do this instead?
For example, yeah, or for example, it will. Okay. So let's say that there is no library function, library implementation for the thing that I'm writing.
Right.
Mhm.
But so this tool will tell me like, hey, you're writing this algorithm. I have the version that is optimized for your hardware with exactly the same semantic like meaning. Do you want and here is the diff? Do you want to apply it? I mean, this will be great, but I mean, it requires a database, let's say, of golden code written by performance ninjas that you can effectively just drop in, replacing in your code, right?
So this sounds like sort of like GitHub Copilot.
Yeah, I was just gonna say, what were your thoughts on GitHub Copilot? I mean, I know that's not necessarily targeted at improving performance, more just improving programmer productivity, but it's kind of on the same lines as what you're talking about.
Right. Yeah. So this I think will be great, and in order to solve that, we need to solve the code similarity problem, like right, like I mean, how we can detect whether the two pieces of code have the same semantic meaning.
Right. And or do they differ in ways that are intentional or accidentals? Like, hey, yeah, you start at 1 and go to n+1 versus 0 to n, but they're near enough the same. Or is that important for some other reason? Right. That's a tough problem to crack, and also not annoying the programmer. I know from my own personal experience, if a Clippy-like thing popped up every time, I would probably, I don't know what I'd do, but it wouldn't be very pleasant to my computer. But it's interesting that you think like the next wave of improvements will come from tooling, which will help programmers write things more optimally. Is that a fair characterization of what you said?
I think yes, because so so some of the problems are just some of the transformations that can improve performance of the code are just so hard to do from the compiler perspective. Like, for example, AOS to SOA transformation, like arrays of structures to structures of arrays. That's something I think that's not easy to do on the compiler level. Like, you need to have the whole view of the program. You need to know whether someone has some references in between of these data structures. So you need to do really complicated analysis and to make that happen. So this is something that much easier can be done on the software level by the developer himself or herself. And so if we would give the better tooling, and we will be able to detect that such transformation can be made or should be made, then I think this will be much more effective, spending of our time and resources as a compiler developers, as a tooling developers.
That makes a lot of sense to me, actually, now that you've put it in those terms. I mean, like the thing that I've always wondered is if it would be possible for compilers to like reorder private members of class structures to move things that are, pack better or more cache effective or whatever like that. But obviously, there's definitely a point where you can't do that without there being changes to the behavior of the program, which are visible, but maybe not important. But the compiler can't make that distinction. The programmer can. And so those kinds of things are really, that's fascinating. No, that's. It sounds like a sort of a different way, like you not really part of, as you say, it's a tool. It's separate to the compiler. You kind of fire up your program in it and sort of maybe get some PGO style samples in and say, okay, recommendation system, tell me what the heck I should do here. And it'd be like, yeah, have you considered moving these things closer together or that kind of thing? Right. That's exciting. Yeah. What an exciting world we live in. But
I guess short of having like tooling that can do that, I guess the only thing we can do is have better education, right? For the developers. Better
education. Yeah. Well, I mean, that's the mission that I'm on, but but at the same time, I don't know. I mean, I'm not sure if we would want to be in a world full of performance ninjas. I mean, well, I mean, we don't want to require to make this as a requirement, right? So that's why I think we need to have better tools and better compilers, maybe, because I mean, performance is hard. Performance, So it's a huge topic, and I mean, I would say that. That it's I think it's easier and will be more forward looking if we will focus on more better tools and developer productivity and allow them to have more insights in the performance of their code.
So something that I always think about when I think about performance is that sometimes performance is genuinely a feature. Like, it absolutely is important that this is critical as fast as possible. I mean, I spent a decade working in the trading industry where that kind of thing is kind of why they're interested in me. But there's always an antagonistic. I believe there to be an antagonism between performance and sometimes readable, testable, lovely, beautiful code, right? And I've spent like the last 5 or 6 years trying to argue that the compiler mostly lets you do the left-hand thing of writing nice, readable code, but it still generates really optimal code on the right-hand side. So, you get the best of all worlds. But the kind of things that you're talking about here is that maybe I'm going to have to change my tune in the next few years because we're going to reach the point where the compiler can't help you anymore, right? We've done everything we possibly can. We've inlined everything we could inline. We've pulled everything out. And the last thing you're going to have to do now is take your lovely class that looks lovely and is modeling a real world object and then split it into 3 little classes that are in 3 different arrays somewhere, which makes it a very different proposition. To what extent do you think that's true? Is that the case, do you think, or am I missing something here? Is there?
Well, no. I think you can have the best of those 2 worlds, and I think that you only need to go for ugly, let's say, performance optimization tricks in those places where it's only needed, right? So I think there is no contradicts here. So yeah, you just first profile the code and you see where are your shortcomings and then you fix those. And then sometimes even the simplest and cleanest code might be not the best code. Like, for example, if you take a look at the std max and min functions, right? Sometimes the compiler will likely generate the branches for you. Like, if it will say like if A is less than B, then I choose B. Otherwise, I will choose A. So compiler will usually generate branches. But what if this branch mispredicts? Then you better go for a C move instead of the branch. Well, okay. Anyway, so it's too much detail here, but
it's okay.
I don't know. I think these are important distinctions, right? These are the kind of things that, if you're interested in these things, but there are trade-offs there that I think compilers don't necessarily know how to do. Even experts, I've seen Chandler Carruth did a live presentation at CppCon one time, and he was like, I don't know why this is happening, and it's like it's generating a CMOV, and I keep going, don't generate the CMOV, generate the branch, for God's sake. And he's like fiddling around with the code, and eventually he profiles it and goes, no, the CMOV was actually, the branch was the right thing to do in this case because it was absolutely predictable, or whatever it was. I don't remember the specifics, but like, these things are hard, and they're maybe data dependent. They may be so so you're saying that stud max might be generating branches or not, and that might not be something that you want to do in all cases. I'm sorry, I interrupted you, so please carry on.
Yeah. No, that's exactly what I meant. Yeah. So, but again, so as I said, right? So I think that you only need to to sacrifice the readability of your code on only those places where it really gives you any benefit. Then
right, you need to have the 4-line comment above to justify the one small weird little thing that you did that wasn't obvious, because that's where you're paying for it. You're like, okay, I have to explain the apology comment that says, no, we really do need to do this funny thing here. funny thing because else the code doesn't. And then for me, it's then write a benchmarking test if you can to try and make sure that nobody accidentally undoes that, or a compiler revision doesn't come along and make it so that is no longer true, or whatever it is you're relying on. Try and put a test around it.
Sure. Yeah. This will be great. Yeah.
So your idea about, tooling that could suggest performance improvement techniques to developers writing code, do you know if anyone's working on that sort of thing?
I think yes, and I think actually, so it's I think it's an area of research called machine programming.
Okay.
Yeah, and that's I actually wrote a blog post, I think, about it maybe last year. It's on easyperf.net on my blog. Yeah, so that's let's say high level vision that someday maybe the machines will be able to program themselves.
But hopefully after I've retired.
Yeah, don't put us all out of the job, please.
Yeah.
Well, I was just interested, that we've talked about only in passing some of the things that are in your online course. What is there something you can tell us a little bit? Is there a teaser you can give us? Is it a free course, or how does the course work for performance training?
I would love to. Yeah, sure. So this is a free online course. It is also self-paced, meaning that you can work on it whenever you have time. So the idea is this, that we actually build a set of lab assignments. So at the moment we only have 7, I guess. So those lab assignments, they focus on a specific performance problem. So those are small like minimalistic code samples that experience some performance problem. Then you require to go and fix it. So
right. So they're like mini puzzles almost that you have to solve using the tools and the techniques that you're teaching people in the course.
Yeah, sort of. Yeah. So at the moment we have lab assignments on vectorization, on function inlining, on loop interchange, on data packing, and I think compiler intrinsics. And maybe I missed some. Yeah. So but the point is here is this. Yeah. So this is an online course, right? So I recorded some videos, right? So the idea is that you first go and watch the introductory video where I sort of give an introductory into the specific performance problem. Then you go and try to fix the code yourself. It can take from half an hour to like 4 hours on the lab assignment. Well, I mean, depending on your background and the level of complexity of the lab assignment itself.
Right.
Mm-hmm.
And then after you fix, you can actually submit it to the GitHub. So the course is on GitHub. It's for free, and there is an automated verification and benchmarking attached to it. So when you so when you submit your code to GitHub, it will be automatically picked up by GitHub, and it will benchmark. I want to point out that this is actually a good performance benchmarking. I mean, it's not benchmarking your program in the virtualized whatever environment on ARM or any other low end CPU. So I actually offloaded all the benchmarking into my own Linux box here at my home. So
you're very brave.
I'm very brave. Yeah, I created an image so that if anyone hack me, I will just
Fingers crossed, right?
Reformat everything, and in half an hour I will have a cleanup system running. But I am prepared to that.
But the key here is that because CI systems generally, be they GitHubs or anything you can find out there, generally they're multi-tenanted, they're virtualized. It's very hard to do performance analysis work when you're on a noisy machine, full stop. Even if it's your own, if it's your desktop under your desk, it's hard to make sure that you're not actually monitoring Slack or whatever other thing that's like causing your cache to go wrong. So you've got a system where you take the user's code and you run it in a very, very controlled environment away from virtualization, and then you can give them pretty good results about whether they've made it better or worse or whatever. That's very cool. That's very cool.
Yeah. Yeah, and then in the end, there is a summary video where I explain how it should be done, how it can be fixed, and how you can measure, and so on and so forth. Yeah.
Cool.
Yeah, very cool.
Sounds great. We'll have to check it out.
Yeah. Okay. Well, Denis, it's been great having you on the show today. Obviously, we talked about the book, the blog, and the video course, and we'll put links to all those in the show notes. Is there anything else you want to tell our listeners about before we let you go?
Well, I think no. We covered a lot of fun topics. Yeah, it was great to be here. So yeah, thanks for inviting me.
Yeah, thank you so much for coming on today.
Sure.